What is a control loop in industrial automation? Imagine a system that can automatically adjust itself to keep everything running smoothly. That is exactly what a control loop does in industrial automation. It is a key mechanism that continuously checks and regulates a process variable to keep it at a desired level. This process variable could be anything from temperature to pressure, flow, or level. A control loop consists of three main parts: a sensor, a controller, and a final control element, which is often an actuator. The sensor is the first step in this loop. It measures a physical variable and converts it into an electrical signal. For example, if we are monitoring temperature, the sensor will detect the current temperature and send that information to the controller. Next, we have the controller. This is where the magic happens. The controller takes the measured value from the sensor and compares it to the desired set point. If there is a difference between the two, the controller decides what action is needed to correct it. This could mean increasing or decreasing the flow of a substance, adjusting a valve, or activating a heater. Once the controller has made its decision, it sends a command to the final control element, or actuator. The actuator then makes the necessary adjustments to the process. For instance, if the temperature is too high, the actuator might open a valve to allow cooler air to enter. This cycle of measuring, deciding, and acting repeats continuously, creating a closed feedback loop. From an electrical engineering perspective, control loops are essential. They rely on signal processing and control algorithms to automate processes effectively. The controller is often a programmable logic controller or a distributed control system, which processes the signals and commands the actuator. There are two types of control systems: open loop and closed loop. In industrial automation, control loops are typically closed-loop systems. This means they use feedback to automatically correct any deviations without needing human intervention. This feedback improves accuracy and helps adapt to changing conditions, making processes more efficient and safer. Control loops have practical applications in various industries. For example, in a chemical reactor, a thermocouple sensor measures the temperature and sends that data to the controller. The controller compares this temperature to the set point and adjusts the control valve to regulate steam flow. This keeps the reactor temperature within safe limits, preventing overheating and ensuring product quality. In summary, control loops are at the heart of industrial automation. They integrate electrical measurement, signal processing, and control actions to maintain processes within desired parameters. By continuously monitoring and adjusting, control loops ensure that industrial systems run smoothly and efficiently.